All right, guys, I'd like to talk to you about exponential functions. All right, an exponential function is a function a lot like 2 to the x that we have right here. This is written as an exponential function. And we can evaluate exponential functions just like we've been doing. So f of 0 would be 2 to the 0 power, or 1. F of 4 is 2 to the 4th, 16. F of negative 3, we know that's a negative exponent, so that's going to raise it to the third power, which will give you 8. And then the negative flips it, making it 1/8. And of course, f of positive 3 is just 8. It's the reciprocal when you're doing the negative exponent versus the positive, of course. And we can even think about inverses. Inverses is what do you got to plug in for x to get out 32? In other words, 2 to the what equals 32. Of course, hopefully we know and already have it memorized that it's 5, right? 2 to the 5th is equal to 32. So this inverse here is spitting out the exponent relative to the base 2. 2 to the what equals 32, For the next one, 2 to the what equals the 7th root of 32. Well, 7th root, we know it's a rational exponent. 32 we already know is to the 5th power. This is just going to be 5/7. It's spitting out the exponent. F inverse of 8 is 3. F inverse 5th root of 16 is 4/5, right? The 4th power gives us 16. The 5th in the denominator gives us the 5th root, right? So we can continue. Ooh, some composition of a function and its inverse. So f of 5, well, we know that 2 to the 5th, plugging in 5 for that exponent, is going to give us 32. And then, of course, f inverse of 32 just equals 5, right? Good. Now, we can do the same thing here. F of 2/3, that's 2 to the 2/3 power, so that's the 3rd root of 2 squared, the 3rd root of 4. Now, the inverse asks us 2 to the what power equals that 3rd root of 4? Well, you just get back to 2/3. And if you remember, these functions, as long as you're in the domain and you're nicely defined, these inverses are going to kind of cancel each other out, so that what you plug in is what you get out. They undo each other, just like inverses do, right? F inverse 1/16, 2 to the what power is 1/16. That's going to be the negative 4th power, and this is the 3/4, right? 2 to the 3rd gives me 8, and the 4th root is the 4th in the exponent, okay? Now, this is an exponential function. It appears that our domain, you can pretty much plug in anything. You can plug in positives and negatives and so on. So we can plug in 1. 2 to the 1st is 2. 2 squared, that's 4. 8, 16, 32. When you go over to negatives, they just make you fractions, like 1/2, 1/4, 1/8, 1/16, 1/32. 2 to the 0 is 1. Plugging in a 3rd would give you a cubed root. This would give you a 5th root of 2 squared. This is just 2 to the pi, whatever that happens to be. And negative 3/5 is 1/5 root of 8. And what you might notice about all of these answers is really that all of them are greater than 0. And I don't know of a way right now to make 2 to the x equal to 0. So I'm just going to put down reals greater than 0. And if we plot these values, you notice it goes through 0, 1. That over here with the negative exponents, the values just get smaller and smaller and smaller. And then when you go to the right, the graph just shoots out to infinity. And we get an exponential graph that looks like this. It does have a horizontal asymptote of y equals 0. That's on the left-hand side. But on the right-hand side, it shoots out to infinity. All right, so let's do this one more time, but let's use a different base. Let's use f of x equals 3 to the x. 1 will go to 3. This will be 9, 27, 81, 243. We get 1/3, 1/9, 1/27, 1/81, 1/243. And again, you can plug in 0 to get 1, and these fractions and stuff will give you decimals and fractions and irrational numbers. 5th root of 9, and this is the 3rd root of 3. So again, you can plug in anything you want. Domain is all reals. And once again, all of our y values here are positive and are not going to be equal to 0. So we have rules greater than 0. We go through the y-axis of 1, and the graph is just going to shoot out to infinity. Of course, this looks like exactly the same exact graph that we had before. So then what's the difference about 2 to the x, 3 to the x, and 5 to the x? Well, if 2 to the x looks, like a nice graph like that going through 0, 1, how is 3 to the x going to be different? Well, it still goes through 0, 1, but as you move to the right, for example, at 1, instead of being at 2 units, it's going to be at 3. And at 2, instead of being at 4, it's going to be up at 9. And so 3 to the x tends to be steeper than 2 to the x when you move out to the right. It gets bigger quicker. Well, the same is kind of true on the other hand side. It's kind of analogous, except instead of getting bigger quicker, on the left-hand side, it gets smaller quicker. And the graph goes below, right? And that's your 3 to the x. Well, logically, if we were to move to, say, 5 to the x, and I'll use this green marker for 5 to the x, it's going to also go through there and shoot up bigger. It's going to get bigger faster, and it's going to get smaller quicker. At -1, it's going to be at 1/5, whereas 2 is going to be at 1/2, and the 3 is going to be at 1/3. So you get that kind of a graph right there. All right? So we can say that 5 to the x is greater than 3 to the x, which is greater than 2 to the x. If x is greater than 0, but all of that is switched if we're talking about negative exponents if x is less than 0. And so we have these different types of increasing graphs. All right? Thanks.